Every week, millions of people apply nail polish to their nails, unaware of the invisible hazard drying right in front of them. Standard nail coatings rely on petrochemical solvents and volatile organic compounds, or VOCs. VOCs are chemicals that easily become vapors or gases, and in a salon environment, they are the primary source of toxic exposure. This data shows a stark reality. Because of chronic exposure to solvents like toluene and formaldehyde, the over 400,000 nail salon workers in the U.S. face a 3 times higher risk of birth defects compared to the general population. The problem persists long after the salon visit. Synthetic polymer chains are designed to be permanent. They do not biodegrade when they are eventually washed away. They fragment into microplastics that saturate global waterways. We've tried bio-based alternatives before, but simple starch or lipid coatings lack mechanical durability and the water resistance required to survive daily life. They chip, peel, and wash off almost immediately. This leaves the industry in a deadlock. Achieving professional-grade performance has required high-toxicity chemicals. To break this cycle, we need a complete departure from traditional material science. So, instead of synthesizing new plastics, researchers looked at how nature builds its own armor. They turned to plant-based biomimicry to find a non-toxic way to create structural toughness. In animal horns and hair, protein molecules lock together into rigid grids called beta sheets, creating immense strength. Scientists extracted plant peptides, engineering them to replicate this exact interlocking structure. As the water-based solvent evaporates, the peptides align, tightening into a dense, solid shield. So, this creates a hard film that matches the performance of traditional plastic, but it achieves this durability without using animal products or petrochemicals. By hijacking nature's structural blueprints, we can now grow a coating that is as tough as synthetic polish while remaining entirely biological. But creating a tough coating is only half the battle. Because the formula is water-based, it faces a secondary challenge, preventing the entire shield from simply sliding off a wet human fingernail. So, to solve underwater adhesion, the team looked at the marine mussel. These creatures spend their lives anchoring to wet, wave-battered rocks with unyielding strength. Mussels use catechol chemistry to grip surfaces, forming incredibly strong interfacial bonds, even in fully submerged environments. Researchers functionalized the plant peptide backbone with tree tannins to mimic these marine anchors, allowing the water-based protein to permanently lock onto the nail. This robust interfacial bond ensures the coating won't peel or chip during regular hand washing, addressing the primary failure point of previous biopolymers. By combining keratin-inspired strength with muscle-inspired grip, science has produced a viable high-performance alternative to toxic adhesives. While nail polish is the first commercial application, the underlying science of peptide self-assembly is designed to work as a scalable platform. The cured material contains 0 petrochemicals and 0 endocrine-disrupting phthalates for the 400,000 salon workers in the USA. This technology removes the primary source of reprotoxic chemicals from their daily environment. The material's life cycle is fundamentally different from plastic. Instead of fragmenting into microplastics, this coating eventually breaks down into simple amino acids, the same building blocks found in the food we eat. This safety profile opens the door for medical use because it adheres in moisture and breaks down safely. Also, this technology is being developed to replace toxic cyanoacrylate glues in surgical adhesives in the industrial sector. These plant-based peptides can replace the non-recyclable plastic films used in global food packaging, providing a protective barrier that is completely biodegradable. By replacing persistent polymers with biological nutrients, we can finally move toward a material economy that feeds the earth instead of polluting it. Imagine a world where your nail polish or food wraps return to the soil as nitrogen-rich amino acids for the next generation of plants. Subscribe to help us build a better world with biology.